Welcome everybody in this week's colloquium. Today we have a pleasure to host Michał from Ghent University and Jagiellonian University. So hopefully Michał will be a person that touches both areas that are present in our institute, so gravity, astrophysics, and quantum information. So career of Michał is pretty rich. So he's expert on high energy physics, string theory, holography, about which he will be talking about, and also quantum information. So he did his PhD in Jagiellonian University. Then he was in many places. So University of Amsterdam, Perimeter Institute, Potsdam. He had a permanent position there, had a group, but in the last couple of years, he is affiliated mostly in the University of Ghent. When he realizes his ERC consolidator grant on formalization in quantum field theories. So quite broad portfolio. So we are very happy to have you, Michał. The floor is yours.
Yeah, thank you very much for the introduction. I'm very happy to be here. Jestem bardzo szczęśliwy, że mogę tutaj być. I was last time here at the Institute of Physics of Polish Academy of Sciences about 22 years ago as part of the Krajowy Fundusz na Rzecz Dzieci. And now it's kind of a pleasure to come here as a scientist. I gave several options to choose from to the organizers of the colloquium, and somehow their idea was to have some sort of high-profile publication, whatever it means. So the plan for today is to spend about 30 minutes to give you a broader context of whatever I want to talk about, and then spend 15 minutes talking about a particular publication. The one that was chosen for me is this paper written with Tim Schuhmann, who's my PhD student, and Jacopo Papalini, who's a postdoc at Ghent. And if you get interested in the broader context of whatever I have to tell you, there is a review article that I want to advertise that appeared in March this year, written with many people, in particular with Paweł Zaputa, who's Polish as well, that introduces the subject to a broader audience. So the topic of today's talk is quantum complexity and volumes in gravity. So we're bringing together two different subjects, quantum computing, quantum information science on one side, and gravitational physics, high energy physics on the other side. And I'm going to be talking about the collision, or how these two fields reinforce each other. So let me start with the most basic idea for whatever I have to say. And this is the idea of holography, also known as ADS-CFT, or gauge gravity duality. And this is an idea that dates back to 1997, to a pioneering work by Juan Moldacena. But it's not an idea that comes completely out of nowhere. It's an idea that is very well rooted in the pioneering works by Bekenstein, Hawking, and others from the 70s about black holes and their thermodynamics. And the idea of the holography is the following. So it's an idea that the way we understand it applies to a particular class of universes. And this class of universes looks like big boxes. And these universes are solutions of gravity with negative cosmological constants. So over here, what I'm plotting for you is a pictorial representation of such a universe. In this picture, this time direction goes in principle indefinitely to the future and to the past, and I just truncated it to fit it on the slide. And now, the box structure of this universe, you see in terms of this being a cylinder. And the statement of holography is that gravitational theory in such a universe, coupled to a particular matter field, is actually secretly given or secretly described in terms of strongly coupled quantum system with many degrees of freedom that lived on the boundary of this box. And one can make it quite precise in the language of general relativity and the asymptotic structure of spacetime, what one means by the boundary of this box. Like for all practical purposes for this talk, it's basically just like this blue region that I depicted for you here. So these strongly coupled quantum systems with many degrees of freedom come in several varieties. One thing that you can keep in mind is that some of them are quantum field theories in, say, 3+1 dimensions, so the physical number of macroscopic dimensions, the way we understand our universe, that are certain cousins of QCD, of the theory of strong interactions. So they have a non-Abelian gauge group and are strongly coupled at all scales. So that's why they are called cousins of QCD and not really QCD, because they don't have asymptotic freedom. On the other hand, these theories could be also given by quantum field theories that describe continuum limit of a critical system. So you may think of, at least superficially, of, say, a spin chain, right? And tuning the spin chain to criticality so that the correlation length diverges, right? And then some of these systems living here on the boundary give rise to, secretly, to gravitational description in one dimension higher. And then, last but not least, there is a quantum mechanical model that that became extremely influential in the course of the past years. This is the so-called Sage-Devier-Kitaev model of interacting Majorana fermions. And this quantum mechanical model was recently shown to be a microscopic description of the universe that is two-dimensional, that gives rise to perhaps the simplest instance of holography of all. And what I want to emphasize is what I said earlier. There's been these pioneering developments by Bekenstein, Hawking, and others that were saying that black holes carry entropy, and this entropy is proportional to the area of the event horizon. And now this led people like Toft and Susskind to conjecture the notion of a holographic principle, that is that the area in some number of dimensions, like in our universe, is like a volume in one dimension less. So that, because the entropy of known physical systems scale typically like the volume, not like the area of the boundary. And as a result, like this notion of black hole entropy being the area fits extremely well into this idea of holography, because precisely the microscopic description of gravity is in one dimension less, where the notion of the area of a black hole translates into notion of the spatial volume, and the notion of the entropy can become the standard notion of thermodynamic entropy. So what I want to, and that's also the source of the word holography, that is the gravitational physics arises as a holographic picture from a holographic plate, with the notion of holographic plate being one of these quantum mechanical setups. So this is extremely well established, and I don't have time nor stamina to go through all the instances in which things were shown to work in holography in a precise manner. But the punchline from the slide that I want to carry through to you is that this breakthrough, holography, is actually a fully quantitative relation, in a sense that we can do, at least in some cases, calculations in these quantum mechanical systems in gravity, and what we get is a match including factors of pi and so on and so forth. So it's not, I mean, it's much more precise than the works of Bekenstein, Hawking, and others 50 years ago. Now, when you look at this, you can ask, what is it good for? I mean, like, what one can do to learn from this relation if we take it as it is. And then, roughly speaking, in the context of the literature of the past 20-something years, there's been two directions in which one can go. One direction is that quite often, I mean, in most of the cases actually, performing calculations in quantum many-body systems, in particular in quantum field theories that are interacting, are extremely hard to perform. One can do this in the loop expansion when the theory is sufficiently weakly coupled. At strong coupling, many questions remain completely unavailable to standard methods. And here is what holography proved to be extremely good at, which is to solve for problems in quantum field theory using gravitational calculations, right? So to sort of phrase the quantum field theory problem in the context of gravitational calculation and solve it and make prediction for the behavior of quantum field theory. So if I were to seek for the most powerful example of such an accomplishment, it is certainly the calculation of the shear viscosity. So one of the dynamic transport coefficients, one of the most important, basically the most important one, associated with 3+1 dimensional non-abelian gauge theory, and predicting that the relevant benchmark value at strong coupling is 1/4 pi times the entropy density. And then carrying this lesson to the community of nuclear physicists in charge of colliding ultra-relativistic nuclei at RHIC and LHC accelerators. And the outcome of this is that when people talk about the shear viscosity of the quark-gluon plasma of QCD, they very often express it in terms of multiples of 1/4 pi, so in terms of multiples of this universal holographic result. So what I'm trying to indicate is that there were concrete successes in which holography affects how we understand experiments on Earth. But now there is also like another approach that in a sense is much deeper, which is to learn about gravity. So microscopics of gravity, understanding the quantum physics of gravity has been one of the so-called holy grails of physics. And here, having this fully quantitative relation, we can phrase problems in the context of quantum gravity, in particular in the context of black holes, in terms of problems in quantum many-body systems, and use this intuition to advance the topic of quantum gravity. And this is the direction about which I want to talk about in the rest of my talk. Now, in the context of these developments about quantum gravity, arguably the most important one is a discovery in 2006, so almost 20 years ago, that the notion of entanglement, and more precisely the notion of entanglement entropy, fundamental entropy of a reduced density matrix, in these quantum mechanical systems, has a particularly simple representation in the gravitational description. So let's look at this negatively curved universe, and let's look at its boundary. Now, remember that this is time in a quantum mechanical system, and if we pick a time slice in this quantum mechanical system, according to the path integral understanding of or formulation of quantum mechanics, picking a time slice means picking a state, basically. So when we pick this time slice depicted here as a circle for illustration purposes, that means that we're considering a state in this quantum many-body system. In particular, as this picture stands, which depicts empty negatively curved universe, this state is going to be a ground state of your quantum many-body system. Now, what we want to do is we want to introduce a notion of subregion in this quantum mechanical system. So for all practical purposes, on this slide, the system lives on a circle. And of course, this circle is a realization in the context of quantum mechanical systems living in one spatial, one time direction. But of course, you can generalize it to systems living in 2+1, et cetera, et cetera. So the system is the full spatial volume occupied by your system. And now we're interested in picking a subregion. And the subregion, for example, can be taken as this interval. And I'm going to be calling this interval A. And now the rest of this spatial volume occupied by your system on a given time slice is going to be given by this A bar, by the complement. And now the statement of these two people from 19 years ago is that if you consider a notion of a reduced density matrix associated with this subregion in this quantum mechanical system and calculate its fundamental entropy, then this fundamental entropy, so entanglement entropy of the subregion in a holographic quantum field theory, is going to be nothing else than a Bekenstein-Hawking entropy, so basically area, of a solved bubble, so an extremal surface, that is anchored on the subregion. So what we have to do is we have to consider solved bubbles in this universe and let them be anchored on the boundary of this box on what we call the subregion. And the area of the solved bubble measured in 4 times g Newton, where g Newton is the gravitational constant. This gives us the entanglement entropy of the subregion. And that's extremely powerful and extremely deep, because actually if you were to calculate entanglement entropy in any interesting quantum field theory, it's typically a daunting task. And over here, this just amounts to finding a soap bubble, so like minimizing some very simple functional and calculating its area and dividing by 4g Newton. So that's a very, very intriguing relation that still remains like the driving force for development, yes?
How surprising and if you take holography related in terms of survival. So statement that two together is a statement about some kind of leading order a very big number.
Yes, that's certainly correct. So I think what you're saying is that these ideas all circulate around a notion of a saddle point approximation, and I think this is certainly correct. But what I want to emphasize is that even though like Bekenstein-Hawking entropy is called the entropy, actually it's not really an entropy in terms of by default counting something. It's just actually calculating the area of some geometric object and dividing by 4g Newton. So I think what's really surprising is that such a geometric notion, purely geometric notion, is given in terms of counting something, right? In terms of entropy. And now, one reason why this development proven so important is that there's a sense in which this holographic entanglement entropy, so these soap bubbles, act as tomographic probes of these high-dimensional universes, right? Because what you can do is you can take this subregion, move from one slice to the other, and of course, if the state is the vacuum, that's not really interesting, but if the state undergoes some non-trivial unitary time evolution associated with the underlying Hamiltonian, that becomes much more interesting, right? So what you can do is you can change the subregion, move it from time slice to slime slice, like shift it to the left, shift it to the right, etc., etc. And in this way, you can perform the tomographic probe of this dynamical spacetime of this universe. And that's something that is very interesting, because in this way you learn various things about the properties of this universe. For example, the question if it has an event horizon or not, etc., etc. Now, if you zoom out from this, actually there is something that is really remarkable that happened here due to these developments by other people, because what's happening here is that tools that many of you care about, so tools from quantum information science, suddenly become quantitative tools in the context of gravitational physics and more generally quantum gravitational physics. And that's something that triggered a lot of other developments and gave rise to many PhD theses and many important insights into the physics of black holes. And now I want to run the same logic that I ran before, which is the following. So consider this universe. Consider a time slice on the boundary. Nobody really objected that this time slice on the boundary represents the underlying state. And now what we've been doing on the previous slice was to partition this time slice on the boundary and talk about subregions, reduced density matrices, etc., etc. But what we can also do is we can consider this time slice on the boundary and extend it into this universe, right? And maybe also apply this notion of extremization and define some sort of extremal time slice, but now in the full universe. We can calculate the simplest geometric properties of this time slice in the universe, which would be the volume of this time slice, and then ask a question: if we consider the volume associated with this time slice in the universe, what would be the microscopic interpretation of this quantity in the quantum mechanical description on the boundary? So what I'm doing is I'm starting with the gravitational description. I'm defining a nice geometric characterization of the full time slice on the boundary that I know that defines a state. And now I'm asking what is the microscopic interpretation of this in terms of the underlying quantum mechanical description. And now the conjecture due to Leonard Susskind is that this volume actually corresponds to some notion of complexity, quantum complexity, so something that, that some of you are interested in the microscopic quantum system. And at this level, well, I mean, this conjecture might look quite crazy to you. And what I want to do in the following few minutes is to try to introduce the logic why Susskind in 2014 made this conjecture. And then I'm gonna propose a precise realization of this relation in the context of this paper that we wrote recently. And of course, if you have some questions, like, please interrupt. I will be happy to talk. So of course, the reason why people like Susskind and also myself got interested in this is because this notion of the volume of the universe arises as a very interesting tool that probes the interior of black hole spacetime. So what I'm showing for you here is a representation on a sheet of paper or on a screen here, the Penrose diagram of a black hole spacetime in this negatively curved universe. And now this black hole spacetime is not much indifferent from the black hole spacetime that one is taught in the undergrad education. I mean, here in Poland, in 4th year of studies, I think many of us had the general relativity. And then what one sees there is a notion of one universe, the other universe that are connected by a wormhole. And then in between these universes, what emerges is what we understand as a black hole interior. And now, in this black hole spacetime, because we have these two universes, we have actually two notions of time. The time in the right universe and the time on the left universe. So sort of like this time slice that now I'm going to be talking about is going to be the time slice that connects these two universes, and necessarily it passes through the region inside the black hole, the interior, so the place where the singularity of the black hole exists. And now what's interesting is that if we push these times to the top, as a function of time, the volume of this time slice actually keeps growing linearly in time. And it is the prediction of general relativity that this volume grows indefinitely with time. And despite the fact that this seems to be just a simple property of most of the black hole solutions, this is not something that we are taught about in undergrad. I mean, like, this is a relatively simple geometric exercise from black hole physics, but people before Susskind have either observed it and neglected without trying to give it an interpretation, or just skimmed over it completely. But this is a general property of black hole spacetime also in asymptotically flat spacetimes. Now, the question is why this object is called holographic complexity, why Susskind made a connection with any notion of complexity. And the picture is the following. So it turns out, and this goes back to fundamental papers on black hole physics by Werner Israel, and later papers by Juan Maldacena, that one can think about this black hole spacetime, so-called maximally extended black hole spacetime, as the so-called thermophile double state in the Hilbert space of two quantum mechanical systems that are entangled with each other in a particular way. And now, the time evolution, as I try to indicate, is with respect to two time variables, because we have two quantum mechanical systems, we have two time variables. And now, what you can do is you can take this this Hamiltonian time evolution and discretize it. This gives rise to some of the so-called tensor network algorithms. And then what one can do is one can try to count how many little gates you have in this discretized time evolution. And basically this linear growth of the volume in time could be then associated with the linear growth of the number of gates that you need in this time evolution. So that's not a great argument in a sense that that's not a proof of anything. That's just heuristics. But the connection that this gentleman made was that indeed, like the persistent time growth of this volume should be linked somehow with adding more and more layers of Hamiltonian time evolution into this picture. And this T over here you can think about as T left or T right. It doesn't really matter at this point of the presentation. And now, of course, at this level, actually, some of you who work on quantum information science should protest and say, okay, I'm not talking about any notion of complexity. I'm just talking about some sort of a notion of a circuit length, right? But now, if you really talk about a notion of circuit complexity, then what's possible is that at some point there's going to be some shortcut, and there's going to be a simpler way of representing your circuit in terms of something else. And if indeed such a thing happens, then perhaps like what you're talking about on the gravity side is actually circuit complexity. And many years, about 7 years after this original conjecture, these people came up with a quantum generalization of the volume of spacetime. I don't want to get into the details because that's not very relevant for us. But what they showed is that even though this volume keeps growing in a linear manner for times exponential in the black hole entropy, at some point there is a transition to the regime in which the volume of spacetime saturates. And in this regime, the notion of a classical black hole, as it's predicted by general relativity, breaks down. And if they are correct, then this indicates that indeed this volume has some notion of optimization built in, and indeed it might correspond to a notion of complexity rather than the length of a circuit. And then I'm not talking here, completely out of the vacuum. It turns out that some of you were interested in this already for some time. There's been a very interesting and influential paper by Michał here, which talks precisely about this phenomenon of saturation of complexity, and even more after times that are way, way longer, also a recurrence. So there are lots of interesting connection here with quantum information science. So if I were to set up a goal for whatever I want to tell you, is the first goal for this research program would be to establish that holographic complexity, so like this volume of the universe, is at all about some quantum mechanical notion of complexity of any sort in the underlying quantum mechanical description. Because so far I just provided you, or other people provided you with some evidence and heuristics. It will be very interesting to make it as precise as one can. As precise, say, as understanding of entanglement in holography is at the moment. Now, if one does it, what one would like to do is to learn the rules of the correspondence. So learn the rules, what are the rules of the game in terms of assigning a notion of complexity to space-time volume. And finally, once one knows what one does, it will be very interesting to apply it to learn more about black hole interior and perhaps other interesting quantum mechanical questions about gravity. So that's a natural breaking point to ask if there are any questions so far about this talk.
So if I may, I will ask another one. To what extent your notion of complexity is going to be local, and to what extent it's going to be global? Because in relativity you have things which are local, defined because you've got the geometry locally of this or that. But there are also things which are only defined if you know the space-time as a whole. And this is especially true in these black hole systems.
Yeah, that's a very good question. So these notions are given by, maybe I can try to answer it here. These notions are given in terms of optimization associated with this time slice, right? So what you need to know to perform this optimization is the causal development of this time slice. And in this respect, you need to know more of a space-time than just this time slice. Any other question, comment, thought? Okay, so the argument that I try to convey is that's not my argument, it's an argument by Lenny Susskind, is that you have this Hamiltonian time evolution, and as time progresses, you add more and more layers of this Hamiltonian time evolution, and then like if you measure the length of the circuit, it keeps growing, right? And then maybe on top of this, there comes an optimization, and maybe there are shortcuts and things change with time. But now, on the other hand, you have this geometric picture in which you calculate the volume and you try to see what happens. So let's do the following experiment. Let's consider a situation in which we consider this thermal state, or more precisely thermophile double state. We do the time evolution, and we get some prediction for whatever this holographic complexity is. And as I try to convey it, what it's going to do is it's going to keep growing linearly for a very long time. And that's consistent with this idea that maybe we're counting gates associated with the progression in time on the boundary in the quantum mechanical description. But now what we can do is we can take exactly the same Hamiltonian that we have, so the Hamiltonian of your quantum mechanical description, and we can apply it to other state. Not to the state that describes this space-time, but perhaps the state that describes these two universes that are completely decoupled from each other. I mean, like one being here and the other being here, and they completely don't talk to each other. They are not in an entangled state. They are in a product state. And now, since these universes represent the vacuum, as I drew them, of your underlying quantum mechanical description, they are time translationally invariant because vacuum is an eigenstate of the Hamiltonian, so it doesn't change in time. And now if you evaluate this holographic complexity, in this case, it's going to be completely time independent. So what this demonstrates is that this notion of holographic complexity is not independent from the state that we consider. That is actually presumably not the notion of unitary complexity associated just with time evolution, but it also cares about the state that we start with, right? So we have to include this notion of a state in our construction in an intrinsic way. So that's like the first guiding principle that is there for the future research, that these states have to be important and they have to appear somewhere when we do these manipulations. And the second insight that I want to share is that since it cares about the current state, it should also care about some other state that at this level is completely unspecifiable. But when we talk about the state and some unitary, then perhaps like there's also a notion of some other state hanging around, say the state where we started, like this. So what I want to emphasize is that somewhere in this construction, there has to be hidden a notion of some reference state. And if we have a microscopic understanding of what's going on, we should be able to pinpoint what it is and what to do with it. So two statements, states are important, and then there should be some other state hidden here in this construction and hanging around. So that's basically all that I had to cover regarding the broad picture. And if there are no questions, and please raise your hand if you have any, I'm happy to, yeah, there are two, actually, yeah.
If I understand correctly, your last argument applies also to the Susskind picture, right?
Yeah, it's certainly, I mean, it's an argument about the Susskind picture.
It's complicated, but it is a magic that when this unitary evolution is applied to an eigenstate,
exactly, yeah.
somehow it quote unquote collapses to a stationary.
Yes. That's absolutely correct. Yes. So what I'm saying is that in this Susskind argument, the state has to be included because these notions are sensitive to state.
I just wanted to ask about this reference state. What is its role? Is it just initial state of the evolution, or it's something else? That's
an excellent question. I mean, at this level, we don't know, right? One one question, I mean, like there's one picture that one can draw, and I didn't want to go into it. I skimmed over the slide because I didn't want to waste time. But since you asked this question, in the context of understanding this holographic complexity as a volume of spacetime and length of some circuit, there's been a very influential yet not precise set of ideas about interpretation of this time slice in your universe as the so-called Mera tensor network. And this is, here I drew this Mera tensor network. I don't want to go into all fine details of this construction. I mean, if you want, I can tell you in private after the colloquium on this board. But what you need to know about Mera is that you can think of it as a quantum circuit. There's an interpretation of Mera as a quantum circuit, and this circuit acts on spatially disentangled state and produces in some gradual way a state that has infinite correlation length. So in this respect, like one might be tempted to think about this reference state as some state that does not carry spatial entanglement. And now, if you think about it further, like it turns out that these states in the context of quantum field theories are tricky because they are characterized by infinite expectation value of the Hamiltonian, right? So you have to think about it in some latticized way, but that would be the interpretation that you would have if you follow this logic. Yeah.
Thanks.
Yeah. Okay. So in lieu of time, let me move to our result. So our result is a bit surprising in a sense that all the things that I said so far are correct, but the notion of the complexity that I was alluding to as a possible candidate for holographic complexity was the so-called notion of quantum circuit complexity. But it turns out that the only thing that was so far shown to be related to holographic complexity is another notion of complexity that goes under the name of Krylov spread complexity. And this notion actually is quite late to this literature. It appeared in the context of works on operator growth and quantum chaos, I think in 2018 by some quantum many-body condensed matter physicists. And later was picked up by the community working on holographic complexity in this reference from 2 years ago. And the idea here is brilliantly simple. I mean, it's like a very beautiful idea due to these people and this earlier work on operator growth. So let's consider just unitary time evolution in your quantum mechanical system. So we have some time-dependent state. R here is the initial state. So like that goes back to Michał's question, what to take R. R is your initial state in some sense. And what you do is you add like your unitary time evolution. And what you can do is you can series expand this unitary time evolution in powers of time. I mean, that's something that people do all the time. But here comes an interpretation. So when we series expand it in time, what we're going to get is we get like the initial state. And then we get a state at time, at power t, the first power of time, what we get is we get like Hamiltonian acting on this initial state. And what we can do is we can think about this as generating for us like another state in the basis. So like we take this state as the first state in our basis, and then we apply a standard orthonormalization algorithm, I think it's like Gram-Schmidt algorithm, to create like an orthonormal set of states. So like the first state is this. Then from this one, we create another state that we're gonna call 1. And now here we have second power of the Hamiltonian acting on the initial state, and from this we're gonna create another orthonormal state that we're gonna call 2, right? And we keep going until we exhaust the basis, until like the basis closes, or perhaps we have to keep going indefinitely, right? Like that's possible. And now, if you do this, if you create a sequence of states, the way you can think about time evolution, and that's why they call it spread. So I should explain that this basis is called the Krylov basis. And now they call it spread because you can think about time evolution as time progresses, you keep occupying farther and farther states in this basis, right? Because if time is 0, you just occupy the initial state, so state 0. If you go like a bit forward in time, only these two states matter, right? If you make time a bit bigger, these three are gonna matter, and so on and so forth, right? So like your time evolution basis is like spreading, right? You spread from 0 all the way to state 1, 2, etc., right? And now the notion of Kirillov spread complexity is a very simple notion. It's a notion of the expectation value of this Kirillov basis vector, right? Evaluated in your time-dependent state, right? So basically you ask a question, what is the average vector number in the Kirillov basis that is occupied by your state undergoing time evolution? And it's gonna change in time. At this level, it's a rather intricate quantity to calculate, but you can live with it, right? And that's an interesting quantity, because I didn't say it, but many of these holographic complexity quantities at early times behave quadratically, and as I emphasize this, at late times they behave linearly in time. And indeed, this Kirillov spread complexity, by definition, basically at early times behaves quadratically, and at later times it actually has a possibility of the growth in time that is linear, right? So it sort of fits the boxes in order to be a candidate microscopic interpretation of holographic complexity, of the volume of the universe. And now, what we did in practical terms in the Spiral article that appeared very recently is we utilized the simplest instance of holography. There's going to be a correspondence between this this extremely simple yet extremely rich SYK model, so Sajda-Kitaev model, that is a model of interacting Majorana fermions, and a particular theory of two-dimensional gravity that has a metric as a dynamical degree of freedom, and also a scalar field that is called dilaton. And this dilaton is coupled to the metric using linear coupling, and moreover, it has a rather intricate sign potential. That's why it's called sign dilaton. And now, this theory of gravity has black hole solutions, and these black hole solutions give rise to a linear growth of holographic complexity, right? Like so basically, it provides this theory of gravity that has a microscopic interpretation in terms of this model, has black hole solutions that have all the holographic complexity properties that we are after. And now what we did is we took the definition, the quantum generalization of the volume, and I don't want to dwell into details, but this was the one that was considered in this paper before us, and actually showed, using explicit calculation, that the volume of the universe defined in these terms is actually nothing else than Kirillov spread complexity in your system. And in doing so, what we did is we generalized the pioneering result of these authors from 2 years ago that were concerned with a single point in the diagram of parameters associated with this model to the full two-dimensional plane spread by this model, which is, roughly speaking, all the values of the inverse temperature and all the values of basically the quantumness parameter of the model. So as a result, by now, what happened is we went from one single example of a holographic setup in which we understood what is the microscopic of holographic complexity, what is the microscopic description of the volumes in the universe, to a continuum two-parameter family of setups. And that's basically the state-of-the-art understanding as of today. Yeah.
So, sorry, can I ask quickly? So in this volume, like complexity, you had two parameters, if I remember, like the left and right.
Yes.
And in SYK, like, do you also have like Temorfield double, etc., and like two parameters? Yeah, because you have like equality between those two notions.
Yeah. I mean, like we think about it in the same way. Yes. Yeah.
Okay,
yeah.
so it's like equality for two parameters.
Yes. Yeah. But the parameters that But the parameters that I have in mind are not TL, TR, because the match there is for any values of these parameters. The parameters that I have in mind are the parameters that characterize the state, so beta, that's inverse temperature, and Q, which is the parameter that characterizes the Hamiltonian. And now time is the parameter that characterizes time evolution of the state, right? So like there is a match, that there's been a match before, but now the match extends to all these values of these parameters specifying the state and the initial state and the Hamiltonian. And now, of course, you can ask, what did we learn? Because we went. I mean, it's nice that it was possible to extend it to a continuum of possibilities. I'm almost done. But one interesting lesson is how this state at arbitrary value of the temperature is constructed, and it turns out that somehow this holographic notion of Kirchhoff complexity, what it really wants to do is it wants to take as a reference state the state that is infinite temperature state, build a finite temperature state by applying Euclidean time evolution, and assign complexity to it. So like you have to assign complexity to a non-unitary time evolution, non-unitary behavior, and then keep going, under the standard unitary time and get what you want. Now this T is not temperature, is the notion of the Hamiltonian for this system. Yeah. And now the second insight that might be less apparent for you why this is interesting is that in this model we have a full control over quantum corrections. So what we have is not only the volume in a universe that is described by general relativity, but we also have a control over the setup when there are also quantum fields that propagate in this geometry and do whatever they want to do according to the microscopic Hamiltonian. And what we did is we calculate this holographic complexity as Kirchhoff complexity also in this quantum regime. And it turns out that the first quantum correction to the behavior given by gravity behaves precisely in a way that would allow you to interpret it as a Kirchhoff spread complexity, but associated with the quantum fields living in this geometry. So that like we talk about these quantum fields being in some state and evolving under their own sort of emergent Hamiltonian, and then what this quantum correction to Kirchhoff complexity in the truly microscopic description seems like a Kirchhoff complexity of these quantum fields. So these are two lessons that, or in fact 3 lessons that we got from this match given in the paper. So let me move to the outlook because the talk was supposed to be about 45 minutes. So the one thing that I wanted to convey in this colloquium is that in the past 18 years, we have witnessed an explosion of understanding about gravity that came from quantum information science and quantum many-body physics. And that shouldn't be taken for granted. I mean, like when I started my PhD in about 2006 and 7, I'm like these things were not there, or like this not visible. This all happened in the course of the past 18 years or so. Now, the key notion that triggered this explosion of interest and explosion of results is this notion of holographic entanglement entropy. And actually, this notion is arguably rather well understood. And as a result, like I didn't want to talk to you about the notion that is well understood. I wanted to talk about things that are interesting to do. And such a notion that is interesting to understand much better is this notion of holographic complexity. So the microscopic interpretation of the volume of spacetime or volume inside the black hole. And what I try to convey in this talk is to discuss the context and highlighting some results of a recent paper of mine in which we provided a second quantitative match between microscopic Kirchhoff complexity and the volume of spacetime in a particular model of gravity in 2 spacetime dimensions. There were 2 lessons about quantum gravity. So one of the parts of the vision that I try to outline is that we want to learn about quantum gravity. And one interesting lesson about quantum gravity is that somehow this notion of Kirchhoff complexity cares not only about unitary time evolution associated with just progressing in time on the boundary in your underlying quantum mechanical description, but actually also it cares about the state preparation that seem to be Euclidean in this setup. And furthermore, I elucidated the behavior of quantum effects and tried to interpret them in terms of some emergent bulk Krylov complexity, and that's something that nobody has ever done before. And now, of course, as you can see, there are lots and lots of interesting things to do. In particular, it would be extremely interesting to understand if one can generalize the statement, I mean, like make holographic complexity precise in higher number of dimensions. So for black holes in 2+1, 3+1, etc., dimensional negatively curved universes. And you know, we don't live in negatively curved universe to the extent that we know. I mean, the cosmological observations point towards a small but positive cosmological constant. So of course, one critical question is if this has any bearing for the universes like ours in the future, and that's another outstanding direction. So that's all that I wanted to convey. Thank you.
Thank you, Michał, for a very nice and interesting talk. We have now time for questions, comments to the speaker. Okay.
Thank you for the wonderful talk. My question is regarding the unity evolution you consider, and you equate the complexity with the holographic linearity of the volume. So as far as I remember, any closed system evolving with unitary evolution grows linearly. So how is it so significant or non-trivial? And second question is about the temperature you are considering. Temperature for a closed system which is evolving unitarily does not make any sense. So how do you introduce temperature when the system is closed?
Yeah, thank you for the question. So let me start answering from the second one, because the answer is basically here in the slide. So I told you about the notion of temperature. And what I had in mind, of course, is the notion of temperature that we associate with the black hole, right? And now, in this beautiful picture of understanding the microscopics of a black hole spacetime, of course, like you hear very often that black holes are thermal systems, right? So in holography, in ADS-CFT, what this means is that if you seek for the description of the state associated with one universe, and remember, black hole is a wormhole from one universe to the other, but if you just look at one of these two universes, then in the underlying quantum mechanical description, this one universe is going to be described by a thermal density matrix, right? And this thermal density matrix is going to have some notion of inverse temperature beta. Now, this full state is a closed, unitarily evolving system, because this full state, this full spacetime, the maximally extended solution, is interpreted as a particular purification of the thermal density matrix to the thermophile double form that I've written here. And this is the sense in which the system is thermal, and yet it's closed. This sense is that one universe is thermal, the other is thermal, but both of them are in a pure state in which entanglement is responsible for thermality of the reduced density matrix. Does it answer your second question? Okay. And the first question was about linearity. I think like this linearity should not be taken for granted. I mean, of course, like if you count, you have unitary time evolution and time is a parameter. Of course, you evolved as much in time as time passed, right? So like in this respect, like the statement does not carry any content. But interesting things happen with this holographic complexity. One thing that I did not emphasize enough, but I mentioned this in my talk, was that at early times, in most cases, this holographic complexity behaves quadratically in time, and only at late times, it transitions to a linear behavior and it keeps going linearly. And moreover, there is a way of generalizing holographic complexity by including quantum gravitational effects, by including path integral over geometries of different topologies, as these people have done in which this holographic complexity even saturates, right? And if you think about notions of complexity, and your system lives in a finite dimensional Hilbert space, then the complexity, even unitary complexity, cannot go on indefinitely, because the unitary group is going to have a finite volume. And at some point, if you keep going for long enough, you're going to exhaust like this finite volume of the unitary group, and as a result, your complexity will not be able to grow anymore. And as a result, I think like this linear growth is like just some part of a bigger picture. And of course, like if you take a limit in which the dimension of the Hilbert space goes to infinity, then of course you can keep growing linearly indefinitely. And this is the limit in particular in which we were working with in our paper that I described. Yeah. I'll be happy to talk about it more in private. Yeah.
Okay, so, but maybe we give now space to somebody else.
If there's somebody, yeah.
If there is.
Oh, there's somebody behind you, yeah.
So thank you, very nice talk. I have a question about the definition of this complexity. So in the Susskind picture, I understand that you discretize your time and maybe discretize your space as well, because you don't want to live infinite number of modes. So in some sense, I suppose that this complexity will depend on the number of the discretization. So it is not kind of like, it is well defined with respect to how you do this discretization. Whereas in the Krylov case, it seems like it can be defined properly. So you call both of these complexities, but can you grasp the link between them, because it's not so clear to me? So
I did good. So let me. I think you asked two questions. Like one question was about the link between these two complexities, and the other one was about some kind of continuum limit in time or in space. So regarding the second question, the reason why Susskind pursued this picture of quantum circuit complexity was not that there was a match. It was just that he found some quantity that has the properties that he seemed to be observing on the gravity side, right? But the fact that these two quantities have similar properties does not mean necessarily that they are exactly the same quantity. So for now, like the only thing that we know about holographic complexity for sure regarding the microscopic interpretation was that there are a few cases, I mean the ones that I described, where actually it is Krylov complexity. But what I didn't tell you is that the volume of the universe is just one of among infinitely many quantities that have this property of linear growth with time and other properties that don't matter that much for the talk, but they are not any better or worse than the volume. So what I'm trying to say is that in this space of holographic complexity, actually there are infinitely many proposals that have very similar structural properties. And it's I wouldn't be surprised if some of them actually correspond to Krylov complexity, some of them correspond to some notion of quantum circuit complexity, right? But that we don't know. I mean, like that's just a vague statement at this level of the discussion. Now, coming back to your first question, what you can do is you can, in the context of the circuit complexity, you can discuss it in the context of quantum field theory. In particular, I think in 2018, I had a paper in which we considered free quantum field theory, say free boson quantum field theory. So we put it on a lattice, and we utilized Gaussian techniques, so Gaussian quantum information, to define a circuit and define a notion of complexity and try to see what happens as you take the lattice in space to zero, right? And what we see is that taking the lattice in space to zero, what it does is it just gives rise to a UV divergence, as you expect in quantum field theory. But for example, the time dependence is not going to be divergent. It's going to be some finite factor on top, right? So this UV divergence actually is going to be something that is not going to be sensitive to the state and is not going to be sensitive to how time passes, right? So in this sense, like it's something that you can live with. There is infinity there, but you can sort of renormalize it and get on. Now, regarding discretizing the time direction, over there, I don't have much to say because I'm not sure if people look into this very much. On our side of the community, what people have looked is the so-called notion, the so-called Nielsen notion of complexity, in which you keep the time continuous. But I would expect that for the evolution in time, taking the continuum limit should be possible, and I would not expect to run into big trouble. I would expect to have the finite limit. Yeah. Thank you for the questions. These were very valid questions.
Okay, we are maybe running a bit out of time. Maybe there are some questions from participants online. Are there any? Okay, there seems to be no. Okay, so Michał will be around for some time after the colloquium, so there will be a chance to discuss with him more. And I guess it's time to thank him again for a very interesting talk. Thank you.
Yeah, thank you for coming and asking questions and being here. Thank you. It's a pleasure to be here.